within the Hangout and also on the live stream. I'd like to introduce you to Paul Kurtzen, who is Professor of Computer Science at Queen Mary, University of London. Paul is co-founder of the Computer Science for Fun website. CS4FN launched in 2004 and is based in the UK, but the resources they're offering are truly globally relevant. To prove that, they have around 15 million visitors to the site each year from all over the world, with subscribers to their magazine from over 90 countries. Parts of the site are translated into Italian, German, Chinese, and Portuguese, and there's more to come. During the presentation, if anybody out there watching the live stream has a question, please go ahead and type those into the comments on the Google in Education G+ page underneath the stream, and we'll look for them so that we can put them to the presenter on your behalf. This session is also being recorded, so you can watch it again afterwards. I'll now hand over to Paul, and I'd like to thank him for giving up his time to present for us today. Over to you, Paul.
Okay, thank you. Yeah, so what I'm going to be doing is talking about one part of the CS Fun project, where we go out into schools and give talks where the aim is really to enthuse kids about the subject. So what I'm going to actually do is attempt to do a very fast version of one of those things. So first of all, let me just switch over to the slides. So I'll do most of this while I have slides going on rather than you staring at me. So just let me switch to that. And hopefully you can still hear me, but have copies of the slides. So basically it's a particular way we're going about doing talks in schools where we're aiming to get across computing subjects, but the core thing that we're doing is not explicitly teaching, it's actually trying to enthuse and inspire the kids. But I use the same kind of ideas and the same things in the teaching that I do at university. So as part of my university lectures to undergraduates. So there it's sort of interspersing these things in kind of a more normal style of lecturing. So what we're basically trying to do here is get across a message of one part of it anyway, is that computer science isn't particularly about computers, it's about computation. And the way we're doing this is actually doing things where we're trying to tell interdisciplinary stories. So a kind of key part of it is not just doing workshops where people are doing activities like learning to program a robot or whatever, but using activities that are part of telling a story that makes it kind of more memorable as something about lectures anyway. Researching what makes a good talk, good lecture is actually that it's something that actually has a story. And also what we're trying to do is make invisible computation ideas tangible. So we're trying to use these unplugged activities where we're using sort of physical things rather than doing things on computers to get across computing ideas, and that gets across this idea as well that it's about computation, not just the technology. So what I'm going to try and do here is give a very fast version of one talk that we do to give you the sort of feel of the kind of thing that I mean. And what I'm going to do is focus on the story side. So when I'm doing this live, and I would normally take an hour or so, it's a 50-minute to an hour talk, and there's lots of activities going on along the way, and I'll give pointers to those, but not necessarily do the activities, though I might end up doing some activities with the people that are live here if I feel thinking we've got time. And we've got resources for a lot of the activities we do actually on the CS Fun website. So there's a section /teachers off of the website where you'll get links to articles that go with these and activities that resources that you can download, and we'll be putting more especially linked to this. But let me get on with the actual talk. So what I thought I'd do is I'd take one of the talks we do, which is based around real-world problem solving. So it's a talk called Searching to Speak, and it's actually about locked-in syndrome. So how would you go about helping somebody with locked-in syndrome? So somebody with a disability, but it's basically the worst disability I could possibly imagine, and it's been in the news quite a lot recently. So what do I mean by locked-in syndrome? Basically, it's where somebody has a stroke and wakes up in a hospital bed totally paralyzed. And if they're lucky, they may be able to blink one eyelid, but basically got no movement at all. But they can see and hear and think, but they can't do anything to communicate back other than if they're lucky, maybe blink an eyelid. So it's as I said, about as bad as I can imagine. You've essentially got an intelligent mind that's completely trapped inside a useless body that you can't do anything with. And so what I thought I'd do is sort of talk about how somebody thinking about computer science ways of thinking might go about helping somebody with locked-in syndrome to communicate. So it sounds like actually that's pretty dire and you can't do an awful lot, but actually one person who had locked-in syndrome ended up writing a book from his hospital bed with locked-in syndrome. So he didn't recover. Generally, people with locked-in syndrome don't actually recover at the moment. But he wrote this book. It's described as the greatest books of the century on the cover. And it's basically his autobiography of what his life was like with locked-in syndrome. So the immediate question you want to ask there is, how on earth did he do it? And if I just switch back momentarily, so I've got a copy of the book here, and it is actually, perfectly normal book. It's 140 or so pages or so, and he basically wrote this book with locked-in syndrome from his hospital bed. He had a helper there with him, who basically acted to take down his dictation, as it were. So the question here, and this is what I would do to the audience, is, so how did he write the book? Well, anybody there got any ideas? So how do you communicate a book when all you can do is blink, and you've got a helper there? Anybody any ideas? I'll just switch back to the slides again. So how did he do it? Well, there's lots of ways you could think about communicating, but essentially the helper just had to read out letters of the alphabet. So they basically sat in the corner and said A, B, C, D, E, until eventually they got the letter he was thinking, and then he would blink, and then they would write down that letter, and then they'd start again. And so if you go to the sort of beginning of the book, it starts, through the frayed curtain at my window, one glow announces the break of day. How did he communicate that? He basically started at the beginning of the alphabet, so the helper went A, B, C, D, E, all the way up to S, T. When they got to T, he blinked, they wrote T down, started again, A, B, C, D, F, G, H, got to the H, he blinked, wrote the H down, and that was the whole of the book. The whole of the way that book was written was doing that over and over again. And that's not just the book, that's everything about his life. So talking to the doctors and nurses, talking to his friends, talking to his relatives, that's the way he had to communicate. And so actually, again, if we were doing this live, I would get the audience at this point to actually try and do that. What we do is we get the sort of pairs of people that are out there to I think I disappeared then. I start back again. Can you hear me again? Okay, so what I'd get people to do is actually try that themselves. So get into pairs, and one person actually has to communicate a word or a phrase or something to the other person, and the other person just goes through the alphabet A, B, C, so they actually get an idea of what's actually going on. And how difficult it is the main thing. So actually sort of doing the exercise will help people really understand what the problem is you're trying to solve. And then the next thing is to then actually ask, so what are the problems there? You've had a go at this. And so usually people come up with the idea that, well, you've got this problem that you can blink when you didn't mean to. And so you've got the problem there you've got to build into your algorithm. And we talk about this, it is actually an algorithm, or you can think of it as a communications protocol in computer science terms. So what you would do is have to come up with some way of backtracking and saying, no, I didn't mean that. And he actually talks about this in the book. But you might have sort of say, okay, if I blink twice, then that means go back, I didn't mean that letter, or start again. So that's one problem. You can also start thinking about, oh, there's punctuation in here, so how did he communicate the punctuation? So you've got to add that onto the list. And so you can start modifying the algorithm, modifying the way that you're doing this to make it actually work in practice. You can also ask, how can we make it better? And so people can usually come up with ideas about predictive texting, for example. So take ideas from their mobile phone, and this lets you talk about one of the computational thinking ideas about taking solutions from a different problem area and applying them somewhere else. So predictive texting works for phones, and it also potentially would work here, where somebody's spelt out the first letters of the word and there's only one word you can imagine it could be, so you can just suggest that and let them decide whether that's the thing that you were thinking of or not by blinking. And again, he talks about that in the book as being one of the way things were done. But you can actually now get into something more explicit about how fast it is, because we can kind of start talking about the efficiency of algorithms and efficiency analysis. So can we actually put numbers on this? And actually you can. If you sort of go to the book and count up the number of letters in the book, if we can work out on average how long it takes to communicate one letter and multiply that by the number of letters in the book, we've got an estimate for how much effort it took to write or dictate the whole book. So we only need to concentrate on one letter. If we're concentrating on one letter, then we can ask things like, so in the best case, how long would it take? Well, if the best case is clearly the letter A, and it only takes one question. So we can think about questions rather than the time. How many questions do you actually have to ask? How many letters of the alphabet do you have to go through to communicate the book? And if the book was all A's, then basically you can just multiply the number of letters in the book by 1, and that tells you how much work it would have taken to communicate it. You can ask about the worst case. So if we're just talking about letters of the alphabet, obviously the worst case is Z, and that's 26 questions to get to that. So a worst case in how much effort went into communicating the book is multiplied by 26. And obviously a much more useful thing is actually the average case. So on average, the A's are cancelled out with the Z's and the B's with the Y's and so on. And so on average, it's about 13 questions. And usually with an audience of kids, they can kind of work through this. They'll give you the answers to this as you go along. So we've actually got an answer to the question of how fast is it. On average, it takes 13 questions for every letter, and at worst, it's 26 questions. Now, in the book, he actually describes an improvement that they came up with, a slight variation on the algorithm, and the idea that they used was to use frequency analysis. So we can have a side sort of story about frequency analysis and what that is, but essentially, ordering the letters that you're asking, depending on how common they are in the English language. So what is the most common letter of the English language? In general, people can tell you the answer E is actually most common. So you shouldn't be asking the question, is it A first? You should be asking E. And so work out what the frequency of each letter is, put them in order, and ask the letters of the alphabet in that order, and you'll end up doing, on average, better than 13 questions, because more often than not, you'll be getting the answer in the first half of the alphabet rather than waiting till the second. And there's a side story here, actually, about Mary Queen of Scots, who was the Queen of England. Oh, sorry, not Queen of England. Scots will hate me for that. The Queen of Scotland.
We've just lost Paul there, but I think he'll be back with us in the next 10 seconds. Must be something to do with the Scots joke. And he's back.
I'm back. I think that must have been the Scots booting me out. Oh, there's a story about Mary Queen of Scots. Basically, she was beheaded by Elizabeth I of England because she didn't know enough computer science. Basically, she didn't know about frequency analysis. But that's a whole extra story that I'll have to tell at another time, because we don't really have time now. So you can go off on sidetracks like that, talking about other things. We can talk a bit more about frequency analysis. But that actually doesn't improve things completely. Basically, the worst case is still 26. There's still some letter that you could be asking about that ends up being the last letter of the list. And actually, as any computer scientist actually knows, you can actually do this in 5 questions at worst. So we're talking about, oh, on average it's 13 and at worst it's 26. If you ask the right questions, you only actually have to ask 5 questions to get to any letter of the alphabet. And at this point I'd ask the audience if they knew how, and usually maybe there's 1 or 2 people think they know this, they've come across the way you would do this. But the point is that actually everybody knows the right question, but only if we do this same computational thinking thing about switching problems to another problem that we already have an answer to. And the way you can do that is switch to the game of 20 questions. So at first sight that seems like it's a completely different thing, it's just a game, but it is, it turns out, a way of seeing that we actually know the answer to this question of what are those 5 questions. So actually, if I switch back and let's actually play a game, if the people there want to kind of do this with me, you'll have to put your mics back on to do this. But so what is the game of 20 questions? I basically think of a famous person and you have to work out who I'm thinking of. But the twist is all I'll do is answer yes or no. So we won't have time to play a full game, but just what really matters and why we'd be doing this with an audience is to get them thinking about what kinds of questions that they ask. So I'm thinking of a famous person. Somebody asked me a question.
Is she female? Is it a she?
Is it a she? Are they female? No. Another question.
Are they still alive?
Are they still alive? Yes.
Are they European?
Are they European? No.
Are they American?
No. So we can go through the continents here.
Are we limited to just 20 questions?
Yes, and I think you're on about 4. I haven't been counting, but...
That was the 5th.
Well, that was the 5th. Jonathan was counting.
So we've got a female, non-European, non-American.
No, male.
Sorry. Even.
Anyway, we can carry on going through this. You would have 20 questions, and if I was doing this with a real audience, then I'd go right through to the end, and they can work it out. And you always get to the answer in 20 questions. In all the time I've been doing this talk, the class has never failed to get there. So the point is not so much the game as what kind of question did you ask. So what was the first question you asked, and was actually that a sensible question to ask? Was that the best question to ask? So what is the properties of it? So if I go back to the screen show again. So the interesting thing is what you didn't do is ask questions like this. So you didn't ask questions like, is it Jessica Ennis? Is it Will Smith? Is it Gandhi? Is it Adele? Is it? You didn't even think about asking questions like that. You went straight to a question, actually, and I put on the slide the one that you did do, are they female? And so the point about that is, why is that the kind of question you ask? Because whatever the answer, it rules out half the population. So it doesn't matter. It's not leaving it down to luck. You're not kind of trying to be lucky style of luck. Look, whatever happens, you rule out half the population. And actually, that's a really good thing if you can keep doing that. So to play 20 questions really well, what you've got to keep doing is asking that kind of halving question. And actually, if we think about it, let's suppose I might have been thinking of 1 million people at the beginning, and if I keep asking halving questions, so how long would it actually take? So, you know, I ask 1 question and I'm down to 500,000, 500,000 people. 2 questions, I'm down to 250,000 people. 3 questions, 125,000 people. So let's make it easier for myself. 64,000 people, 32,000 people, 16,000 people, 8,000 people, 4,000 people, 2,000 people, 1,000 people. After 10 questions, there were only 1,000 people left out of those million that it could be if you always managed to ask halving questions. So keep going. 1,000 people, we're down to 500 people with 1 more question, 250 people, 125 people, 64 or so people, 32 people, 16 people, 8 people, 4 people, 2 people. And on your 20th question, there is only 1 person left it could possibly be, if you could always ask perfect questions. And so what we've got there is a massively fast way of doing it. And if you think about comparing that with what we were talking about, is it Jessica Ennis, is it Will Smith, is it Gandhi, on average, doing it that way it would take 500,000 questions on average. But now if we go back to what we were actually talking about before, and letters of the alphabet, we're saying 1 million people I could be thinking of with yes/no answers, then it's going to take me, at worst, 20 questions. But with 26 letters of the alphabet, for some reason we were saying it was going to take us vastly longer, on average at 13 questions, but the worst case would be 26 questions. And what's going on? We're just asking the wrong kind of question. So what we were doing is doing exactly this of, is it this, is it that person, is it the other person? You know, that's exactly what we were doing. We were going through, is it A, is it B, is it C? And so what we actually want to do is ask halving questions with the alphabet. And so switching back now, we've got the solution from this problem of 20 questions that we all do know how to play, because everybody always does ask the right kind of questions when you're playing this game. If we switch over to halving questions, so I don't know whether you can see well enough on this graph, but essentially it's just sort of saying, here are the questions you would have to ask. Does it come before any in the alphabet? Go halfway, and then depending on which way you go, you're then asking, is it before F or is it before T? So halving what's left. And if you keep going down these questions in the graph, eventually you'll get to one of the letters of the alphabet and you get there in only 5 questions, whatever happens. And actually I've optimized it so that you can get to E in less than 5 questions as well. So by looking at the way we were playing that game, looking at the solution we had already, you can just apply that, and it works for this other problem, because it turns out the problem is exactly the same. And what we're actually talking about here are what computer scientists would call algorithms. We've just actually looked at 2 ways of searching for information, something that Google presumably know a lot about. So 2 very simple algorithms for searching for things. Do you just line up everything you're searching through and check them one by one? Is it A, is it B, is it C? Or do you look for this halving thing, do what is called a divide and conquer algorithm, and essentially you're doing what would be called a binary search. You're splitting the possibilities in half and then splitting them in half until you're down to the one you have. And as we've seen, you get something that's massively faster. And if this is the point, so far we've not been talking about anything at all to do with computers and technologies themselves. This is just about ways of doing computation. So we're talking about one person just talking to another. Jean-Dominique Bowlby, who wrote the book, didn't actually have any technology there. He did just have himself and a person sat in the corner of the room. But what we've got here now is potentially a much better way of him communicating, because actually he can get to a letter of the alphabet in only 5 questions at a time. So that suggests we've made his life massively better. At this point, once we've talked about algorithms, we can then go on to technology. But the point is, if you're using the wrong algorithm, the technology will still be slow whatever you're doing. So, you know, you can talk about implanting brain implants into people's scalps and sort of reading their minds. You can use vision technology to sort of record blinks and detect when people are making blinks. So you don't necessarily have to have the human there now, but you've got to get the algorithm right first. And then you can go off on another side story. We're talking about the technology now. You can sort of talk about cyborgs and so on, and plugging people in, putting chips in them, whether it's in their brains or elsewhere, and reading their thoughts and so on, and actually you're developing superhuman powers. But the point here is, what we've done is come up with a solution that I hope everybody agrees at this point that actually is a way of making somebody's like Bobby's life massively better. He would have been able to communicate massively quickly. Instead of, in the worst case, 26 questions, it's only 5 questions, and that's the worst case, not on average. The book would have been much easier to write, and talking to his friends and family and the rest of it would have been easy. So does everybody agree with that? Well, usually with an audience everybody does. But at this point I would point out that actually you're probably wrong. Or you might be, because we came up with a better solution, supposedly 5 questions, not 13, but we might not actually have been counting the right thing. What if blinking's hard work for him? Our solution actually is 5 blinks that he has to do per letter. And if he finds blinking hard, we've just made his life a lot worse. We've made it harder for him to communicate. So even though if we were counting the right thing, it is a better solution, unless we know the answer to the question, is blinking hard work or not, we don't know whether we've made things better or not. And that's ultimately this was in part a story about algorithms, but actually it shows that computer science is really about understanding people. And if you don't understand the problem you're trying to solve, and that means understanding people, then you may solve the wrong problem. And if we then went on to say, okay, get rid of the person, put a computer there, we may have removed the thing that gave him a reason to live, because he might have decided to write the book just because he wanted a person there. We might have made things a lot better. He can now tweet, he can blog, he can do all the rest of it. But the main message here, computer science and electronic engineering and the related subjects are actually about understanding people as much as technology. And once you've realized that, if we go on to the last thing, you can then start thinking, well, actually communication is actually a lot more than just about the words you say. So maybe if we're really trying to solve this problem, we ought to be looking to help there too. So I just want to finish by showing you a video, because you could be thinking about, well, can we make computers give a way of communicating in these other ways, with body language, with emotions and tones of voice? So let me just switch over to this video. This is basically a video of one of our student projects. So this is just one of our third-year students did this as his final year project. So this little robot that he's made has a neural network brain. So there's a story there about what neural networks are. But essentially what it's doing is not understanding any words he's saying, it's just reacting to the tone of his voice. So if I start the video, so he talks softly to it, and it's a fairly happy robot, but when he starts getting angry with it and the tone of voice changes, it will start to look unhappy, and it gets sad.
But stop doing that, that's right, silly robot, you stupid robot. Okay.
And then he'll talk softly again. It's a bit like talking to a dog. And it'll realise from the tone of his voice he's happy, and so he'll start to cheer up. It can be surprised as well. Watch its eyebrows in a moment.
Sometimes I've just had enough of you, you silly robot. Get out, I'm sorry, I didn't want to. I'm sorry. Smile for me, please. That's good.
And then he calms it down again by talking gently to it again. And so what that's showing is basically that human communication isn't just about the words. We're understanding a lot about what the robot's thinking and feeling, if it was really thinking and feeling, from just the emotions. And that's a very cartoon version of a robot, and we're still getting quite a lot from it. But the other thing is, it's showing the robot can get a lot from just the tone of his voice without having the words there. And so in fact, we're actually trying to kind of create communication systems for people with locked-in syndrome. Maybe the next step, once we've sorted out ways of them communicating with words, we want to actually start thinking about how can we communicate these other things. Can we actually give that wider experience of all the rest of it? So at this point, I'm kind of wind up. Just go to the last slides here. Essentially, the message of this story is, before you come up with solutions, you've got to understand the problem. And that usually means understanding people as well as computers. And this is something computer scientists do. They rush in and they think they've got the solution, and they do solve it. But the backstory of that is actually these computational thinking ideas of using things that we know about as a way of solving problems. We sometimes know the answer, we just pull a solution from elsewhere, and we've got a solution to a new problem, is one of the things that computer scientists do. But ultimately, computer scientists is sort of thinking out of the box. It's all about doing things better, doing things that couldn't be done before, about improving life for people and ultimately changing the future. And that's basically what the message of that story is. So at that point, I'll finish. I'll leave you here with links. So Computer Science for Fun is actually, the website is CS4FN.org, and from there you can kind of get to all of our online activities. You can also order things like class sets of the magazines. There's resources for teachers in a directory /teachers off of that. There's a link from the side of the main web page. Other activities that are these kinds of unplugged activities, like playing 20 questions as a way of doing divide and conquer. There's sites like CS Unplugged and CS Inside that actually have a lot of other activities like that. But the thing that I really want to get across here is not just the activities that matter. If you can embed activities in a story that makes sense, then it actually makes it a much more powerful story that you're telling, and that makes it memorable, and it gives the students the hooks to actually hang on to actually allow them to remember the stuff that you're really trying to teach. And at that point, I'll finish. So thank you very much. So any questions, I guess, at this point?
Yeah, I've got one, Paul. We're talking there just at the end about things that you can add to stories to make them more effective. But I was wondering what you thought makes a good story in the first place.
Okay, so the main thing, so what I mean by story isn't necessarily a story in the sense of what you would find in a short story, but it's something with a narrative. It's something that's sort of connecting things together. I think the most powerful stories are ones that almost work in the way a short story sense. So they've got to have a narrative. It's not just a series of facts that you're just giving to people. And I think it works best if they're interdisciplinary. They're pulling in lots of different subjects because that gives it a wider reach. So this one is a lot more focused on one subject area. Other ones that we do are pulling in psychology and philosophy and even the arts into the stories that they're telling. You also need something, a hook at the beginning of the story, so a grab that actually gets people's interest right from the start, something that sort of makes you sit up and think. And I like this story for that, because I can't think of a better grab than the idea of thinking about what it's like to have locked-in syndrome. But ultimately, what really matters with telling this kind of story, and the ultimate thing about trying to enthuse and inspire students, what matters most is you're enthusiastic yourself, and it's your enthusiasm, and in the end ends up being infectious, if I could say the word. So you just infect everybody with your bouncing up and down enthusiasm is the idea. But the core thing is really having a narrative, that's something that's connecting, and you can go off on side connections, which I didn't do here, but I was mentioning some of them, like the Mary Queen of Scots story, and each of those are sub-stories within the story itself. But essentially, it's things that are about people, really, are the things that make the most powerful stories, I think. Okay.
Yeah, thanks.
Another question? I can see on the slide here, Laura was asking, didn't Stephen Hawking use something similar to this? So yeah, originally, so he didn't have locked-in syndrome. He had a sort of degenerate condition. So originally, I think he had movement in his fingers. So he was actually controlling a joystick, I think, with his fingers originally. And then his conditions degenerated. The system he's used has been adapted, I guess. But what he has, in the sense of the paralysis that I'm talking about, isn't as bad as locked-in syndrome. So locked-in syndrome, you really can't move at all, so you wouldn't be able to even have small movement of your fingers to be able to move a joystick. And some of the people who aren't lucky can't even blink an eye, and so there's cases actually in the UK press at the moment stories about people who've had locked-in syndrome and they've had no way of communicating, and people have just believed that they're in a vegetative state. I think there's a case in the US at the moment where they've actually just used a brain scanner to find that somebody actually can communicate. There is somebody in there, as it were, and that actually links into this. So they're going to have to, or they will have come up with some way of communicating with him. But ultimately, you've got to come up with a communication protocol. And if you come up with a way of communicating that is slow, it doesn't matter what technology you're using, it will be slower than it could have been if you thought through the algorithms first. So Laura was asking, so how would you suggest getting more girls to explore computer science? So I think the thing that matters the most with girls is not focusing on the technology as such. So to some extent, this is playing on a stereotype, but what I think helps with girls more than boys is being able to see the end result. So I think this kind of story works really well with girls, rather than just saying, look, here are robots, play around with these robots, here are things you can do. Give them the end result. You know, if you learn some computer science, you'll be able to help people in this way, you'll be able to do these things, and then sort of work back from that. I mean, we do have a whole area on the CS4FN site that actually is specifically about women in computing and the things that they're doing. And to some extent, this is what computer science for fun is about. It's about telling stories. We try and write articles that are telling stories about people, and we do have quite a lot of stories about the research that women are doing. and having role models like that, I think, really matters, and having more than just the standard one or two that people keep churning out over and over again, that shows actually there are lots of women out there that are doing computer science. It's not just an odd star here or there, it's just everybody's doing it. There are less numbers at the moment than men perhaps, but you know, there's still a large number of women, and here are all the interesting things they're doing.
Great. So thank you very much, Paul, for that really great presentation, and thank you to everybody who joined us there on the live hangout and also watching the stream. Just to remind you, this broadcast has been recorded, and you'll be able to find it on the Google+ Google in Education page, and also on sites.google.com/sites/eduonair. We've got another one tomorrow, same time, same place, on the magic of computer science, also from Queen Mary, University of London. So we hope to see you there tomorrow. Have a good evening.